Welcome to Mrs. Mahoney's podcast. This is our first one of Unit 10. It's the Unit 10 packet, but this information can also be found in Chapter 15 in your book, and don't forget that's just an additional resource. We're going to be talking all about solutions. And what is one of the most common solutions? The ocean. That's why I had the picture of the ocean up here. It really is just salt water. Water is your solvent. Bunch of stuff dissolved into your water. That's what we're talking about, solutions. So let's talk in the beginning about that solvent, water. Okay, so it says draw the Lewis dot. I have it here in a nice picture. If you were just drawing it, what do we know? That oxygen has 6 valences. It wants those 2 more, so it's going to share, has the 2 lone pair. Okay, so what was the name of this shape? That was Panda saying hi. Okay, remember water is a bent molecule because of these 2 lone pair of electrons. The electron geometry is tetrahedral, but the molecular shape is bent because of those lone pair. And don't forget, it's a very polar molecule. And what does polar mean again? That it's uneven distributions. This oxygen, is taking more than its share, so this end is slightly negative, this end is slightly positive. Because the oxygen has taken more than their share of electrons, it's a high electronegativity difference. So that's why it has, it's not quite ionic like an ionic charges, but they do have the slight charges. That is why water has so many of its properties. So on your sheet, it's just worded a little bit different. Yours says, how does the density of water in the liquid state compare to the density in the solid state? So hopefully by reading this, that should be able to answer it. Why is solid water less dense than liquid water? And again, how do we know it is? Well, how do we know? Because ice floats. Remember, ice is just solid water. What does it do? Ice floats. So that means, if something has a less density, it's going to be on top. So that must mean it's less dense. And in fact, the maximum density of water occurs when at 4 degrees Celsius. Just right before it starts to turn into ice, that's when you're going to have the maximum density. This is really rare. Most substances, when they become a solid, as those molecules cool down, they get packed because a liquid, remember we were talking about the particles. We have gases are all over the place, obviously even more than I can draw. So this would be gases. Then you have liquids. What's happened? They're slowing down, that there's a greater attraction. This is why they hold their volume. Okay, then you have a solid, and solids are really packed tightly together, even more attraction between it. So typically in densities, gases have the least density, then liquids are in the middle, and then the solids are the most dense for the majority of substances. Water doesn't follow that rule. That is weird for water. So why does that happen? And it all is about the shape. So let's kind of look at that shape and really what's going on then. Remember the intermolecular force, this hydrogen bond here, that is a intermolecular force, INF, intermolecular force. It's the force between the molecules. So it's the attraction between each little water molecule, and it's because it's so polar that it's like a strong magnet holding those together. And on Monday when we come back, I'm actually have some little water molecules that look like this, and we're going to kind of look at that and feel and kind of look at that strong attraction between those water molecules. So let's look at what's happening. I'm borrowing a quick little video of just kind of showing what's happening at the water. So we have a movie with sound, borrow. Keep an eye on the temperature over here. So right now we're just looking at liquid water, totally random. Molecules, no really order. Okay, as temperature cools down, the molecules start moving slower, kinetic energy. And so what happens, those molecules feel more of an attraction. So it's get water crystals because of that shape. They get frozen into that six-sided shape. And remember that bonding in between it is that hydrogen bonding, which is just really like a super polar. It's a really, really strong polar. And that results in that strong attraction between the water molecules. So however you kind of sum that up to say why the density of ice is less dense than the solid. And really this polar bond and that shape really has a lot to do with why water has so many of its properties, which includes the universal solvent. That high surface tension is why it forms, you can put a lot of drops of water on a penny. That high pulls it in tight together. Water has a really high boiling point. It's a really, really light molecule. It should be, actually it shouldn't even be a liquid at room temperature. And it boils at a really high temperature compared to other molecules comparable to it as far as its size and its weight. Okay, so what is that universal solvent? That just means that water can dissolve so many different things. There's a saying, like dissolves like, which means water can dissolve many different polar compounds. And that's what it says. Like dissolves like means polar dissolves other polar. We're going to talk about this more in a little bit too, in another podcast. But because it's so superpolar, almost charged, it also dissolves many, many ionic compounds. And so that is why it dissolves so many different things, that universal. It's called the universal. So what happens when something is being dissolved? Let's look at this. Okay, and again, borrowing. So we're just adding some salt water to this. So what happens is the water is acting as a solvent, which means that you're dissolving different things. So look what happened. This hydrogen is surrounding it. And opposites attract, which we've talked about before. So this is where the positive end of the hydrogen is being attracted to the negative. And so the negative end of the oxygen gets attracted. And it forms little molecules, the bonds. It's like little shells from it. And so they separate the ionic compounds. So when we say that something is soluble in water or can dissolve in water, then what happens is if water can get in between and separate the ions, if it can separate out the ions, that's how we say something is soluble. All of those compounds we said were insoluble water, they were too big. A lot of times if you look, they're too big and heavy, or they're being held too tightly together, that water cannot get in between and separate the molecules. So some of our vocab as we're going through, these are just this chapter unit, not as much math. Notice I didn't say no math, not as much math, but a lot of the vocab. So a lot of these words I expect you need to know. So I probably even expect maybe a little vocab quiz coming your way. This you may just want to add. Again, if I expect that you know what a mixture is, the definition of a mixture. If you do not know it, write it down. That's that physical blend of two or more substances. But remember, it's a physical blend, so they each keep their own identity. Okay, so then we had two different types. We had a homogeneous and a heterogeneous. Well, really, we're not so worried about the heterogeneous. A solution is a homogeneous. Since our focus most on this is solutions, the majority of the time we're going to be talking about a homogeneous mixture, the solution, which means, again, uniform composition. Okay, I also added the word here, soluble. You need to know what does soluble means. Remember, soluble means it can be dissolved. So if that is what soluble means, you better know what the opposite then is. And if it's insoluble, insoluble means it does not dissolve. Words I'm going to be using a lot, so you need to make sure you understand what I'm meaning. Okay, so again, that solution then is the homogeneous mixture of two or more substances, single phase. What does this mean? They're either all liquids. You can have liquids, you can have gases, you can have solids. So you can have both. You can have liquid, or you can have a gas solution. Air is a gas solution. You can have a solid solution. An alloy is a solid solution. Liquids are what you're most comfortable with, salt water, sugar water, but they also exist in different phases. Okay, so in a solution, you have two different parts. And again, vocab. Solvent, well, we've already talked about water being the universal solvent. So solvent is what is doing the dissolving. There's called the dissolving medium, what is doing the dissolving. Or if you're looking at percentages, it's what there's the most of then. Okay, so solute is what is being dissolved. Sugar water, water is the solvent, sugar is the solute. Look at air. Air is about 80% nitrogen, so we would call nitrogen the solvent, and everything else mixed in would be the solutes. Look at the back of a soda can. Water is, again, the solvent. Everything else being dissolved is the solutes. Okay, when you have solutions, we have different types. Electrolytes, yes, like in Gatorade, is a substance when dissolved in water, it creates a solution that can conduct electricity. You need these electrolytes in Gatorade and in your body because when you sweat out a lot of the sweat. Your sweat is kind of salty. You're sweating out some of your electrolytes. So you need to rebalance those, and that's why Gatorade, if you look, there is ionic compounds in there that help to balance out that. Your body needs that for the synapses, to help your neurons, to help it conduct. And that's why when you are dehydrated, you feel very sluggish, and sometimes it's hard to think because you need to get not just water to rehydrate, you also need the electrolytes. So we say it's a weak electrolyte if there's not very many ions, which means it's not going to conduct electricity very well. A strong electrolyte has more ions, therefore it's going to be a strong conductor. Okay, so a non-electrolyte, it's just what it sounds like. It's not going to conduct because it does not create any ions. So right here, keyword ions, hence ionic compounds are going to be your good electrolytes. And it's again all going to go into solubility. The more that dissolves, you're going to get more ions separated. It's going to be a better conductor. So if we look at this, and let's go to salts. So we look at this conductivity, so we fill in it with some salt water here. And this is what a conductivity tester looks like. We're actually going to do a lab very similar to this when you come back. If it completes the circuit, so if there's ions in here, it completes the circuit, when I throw the switch, it's going to light the light bulb. This means it's a conductor. There's ions in here that are completing the circuit. Okay, that would be pretty strong. Now, I'm not 100% love with this because these are all going to dissolve pretty well, are going to be all pretty good conductors. So I'm going to go over to some bases that I know do not conduct as well. And again, sodium hydroxide, this is a base. We'll talk about it more, but it's also an ionic compound. Okay, look at how brightly it shines. It's a very strong conductor. Compared, we'll start looking at more of these later. Okay, this is a base. Okay, it shines a little bit. So when we talk about acids and bases, we'll call this weak. It really is a weak electrolyte, and it's also going to be classified as a weak base because it doesn't produce very much electricity. But this is what an electrolyte would do. It completes the circuit and it would conduct the electricity. Okay, an alloy then is a mixture, it's a solid mixture. So when we talked about these, your alloy would be then a solid solution. So this is a solid phased solution, and it's a metal and one or more other elements. Typically they're added to make it better, to make that metal better, stronger. For your information, this is just some common alloys. Brass, bronze, coins are a mixture. Okay, and if you look at the uses over here, again, they tend to make them a mixture to make that substance stronger. So, but if I look at sterling silver, down here at the bottom, sterling silver, it's mostly silver, but again, add some copper to give it a little bit more strength. So I would say that the silver is the solvent and copper is the solute. Okay, let's look on, run just the back of the page there. We're just going to be finishing up on page 3. So when I'm talking about a solutions, their particle sizes are so small that you can't even see them. So let's look at the next size of a particle. And again, particle means a solute particle compared to the solvent. So colloids are when I have the medium-sized particles, solute particles. They do not totally disappear, but they do not settle out. They actually are kind of held in suspension. This is a really cheesy movie, but it actually is pretty good.
Mixtures, like paint, are called colloids. A colloid is a mixture in which the particles are mixed together but not dissolved. The particles in colloids do not settle out and are continually bombarding each other. Shaving cream is a foam that is a colloid. Fog and smoke are colloids and appear quite cloudy. The liquid on the left is a gelatin, a colloid. The liquid on the right is colored water, a non-colloid. Due to the properties of the gelatin, light can pass through it, and the particles seen, but the particles in the colored water on the right cannot be seen.
Okay, and you couldn't see those particles because they were so small. The bigger ones in the colloid bounce the light back. That's why, as all of you are learning to drive, if it's foggy, you have them down on low beams. If you have them on high beams, fog is a colloid, the water particles scatter the light. Here are some common colloids. Most of them you've heard about. Milk is actually a colloid. Fat particles suspended in the liquid. That's why you have full milk. You have whole milk, 2%, 1%. That changes the amount of fat particles suspended in it. Cheese and butter are actually emulsions, and the same thing. That's an emulsion is really a type of a colloid. Okay, the Tyndall effect was what that light was. And I'll probably have an example to show you that on Monday. And that's a good way of testing that. If I said, is one a Kool-Aid, what's the difference? If you had a flashlight, that's how you could tell the difference between a solution and a colloid. It's that light, it's the fog, it's the reason you have to have your, again, the lights on the low beam. That's called the Tyndall effect. Okay, the last particle, mixture we're talking about is actually a heterogeneous mixture. And this is a suspension, means now the particles are so big you can actually see them. And they're so big you can actually see them that they're heavy and they're going to settle out over time. So again, another cheesy movie.
A suspension is a heterogeneous mixture in which some of the particles settle out. The particles and the water in this paperweight form a suspension. The water in this raging river also forms a suspension. This flask of water was taken from the silty river. Let's see what happens if we let it stand for several hours. After a few hours, you can see the water is clear and the particles have settled to the bottom. If you look closely, you can see different sizes of particles. When rivers rise over their banks, as seen here, silt and particles often drop out of suspension.
So again, how do you tell the difference? Pretty much if you have to shake it to mix it, that is a suspension. Orange juice, what's the first thing you do? You shake it, orange juice with pulp. Otherwise, by the end, if nobody shook it, you're going to be chewing your orange juice. So last little thing I want you to add, okay, and again, when I'm talking about the particle size, I want to make sure we're clear. I'm talking about the size of the solute particles compared to the solvents, okay? So the solutions have the smallest particles, the colloids are in the middle, and then these suspensions are the largest. So over the spring break, I just wanted to get some of the vocab out and get some of the information so that when we can come back, I want to start with a lab that actually, a lot of these terms, let's see if we can actually see them and start to make sense of them. Have a great rest of the break, or if this is Sunday at midnight, I will see you tomorrow.